Hello, class. Let's talk about a concept called average atomic mass. We've been talking about atoms and mass number, and mass number is, of course, the number of protons and neutrons in the nucleus of an atom. It gives basically the atom its mass because electrons do not contribute appreciably to mass of the atom at all because they're so small. Electrons are so small compared to the size of a proton or the size of a neutron. But when we read a periodic table, we don't get nice whole mass numbers. For instance, if I go to iron on the periodic table, I'll notice it has an atomic number of 26 protons, but it has this number, 55.85. So the question is, well, where does that come from? Well, this is an average. This is an average. It's a weighted average of all the naturally occurring isotopes that we believe that are occurring, and to what percentage we believe that those isotopes are occurring. And that takes some scientific work, and it is a culmination of data over the years. But this is a weighted average, similar to like your grade. Your grade in this class is about 60% of what we call secondary grades and 40% primary grades. So in order to find out your grade, you have to take into account those percentages. Same thing here with the average atomic mass. Let's go through a problem. Let's show you how it works. There are 4 different stable, naturally occurring isotopes of iron. Many atoms on the periodic table have lots of different possible isotopes, but the stability is in question here. How long does it actually hang out for in nature before it decays into something else, which is called nuclear decay and those unstable isotopes, which is a whole other class. But let's just simplify. Let's just say there are 4 naturally occurring versions of iron, isotopes. There's a version of iron that has an atomic number of 54. Well, that means it has 26 protons, and that means it's going to have 28 neutrons, because 26 plus 28 will give me that 54. But that version of iron only occurs 5.8% of the time in nature, as far as we know. And these percentages are adjusted, or have been adjusted over the years when we find out more information, or we find new discoveries. But generally, we believe about 5.8% of all the iron in nature is this kind of iron. Then there's iron 56. So that means that this particular iron would have 26 protons and 30 neutrons. So it's got 2 extra neutrons compared to this one. That's why the mass number is increased by 2. But this version of iron exists 91.8% of the time. So that's the bulk of what iron is in the natural world. Then there's 2 other isotopes which only take up a small percentage of how it occurs in nature. Iron 57 and iron 58. That means that this would have 31 neutrons. This means this has 32 neutrons. And you can see their existence in nature isn't all that great. This one exists about 2.1% of the time. This one exists about 0.3% of the time. And I will tell you that these percentages actually are even rounded. They go on for quite a number of decimal places. But for this particular example, and many of the examples that you're going to attempt, we round these percentages. We try and hope that these percentages add up to be about 100%. In this particular case, it does. And in some of the problems, it might be like 101% or 99%, depending upon the rounding of these figures. It's assumed, though, 100% of the isotopes are basically represented. Well, what we're going to do is we're going to take all 4 of these versions and add them up and average them, and that should be this number, or very close to that number. What we don't do is the following. We don't just take a straight average, right? We do not take 54 plus 56 plus 57 plus 58, add these up and divide by 4. That's not necessarily it's not going to get us the right answer. It shouldn't be that number. Because if you do this, you're going to end up with, in the middle, you're going to end up with 56.5. No, not quite. Hold on. Let's add it up. We got 10, 15, 25. We got 5, 10, 15, 20, 22 divided by 4. That's going to be 56. Well, it's 56 point something. But the point is, you don't just straight average them. No. We have to take the weighted average. That means we have to take into account these percentages. So what we're going to do is we're going to take each isotope and multiply it by its appropriate percent. So we're going to take the isotope of iron that's worth 54, and we're going to multiply it by the percent, 5.8%. But remember, when you multiply by a percent, you have to move that decimal place over 2 plot places, right? Because 5.8% is really equal to 0.058. And you're going to get value. And then you're going to take the 56%. 56%, I'm sorry. You're going to take the version of iron that has a mass number 56. And you're going to multiply that by its percentage, which is 0.918. You're going to take the 57 isotope and the 58 isotope, and you're going to multiply those by their appropriate percentages. Now be careful, this 0.3%, because that's going to be multiplied by 0.003. So be careful of again, moving that decimal place over 2 spots. You're basically taking these numbers and dividing them by 100. And when we do that, we're going to get some answers. So we're going to multiply these across. And if you put them into your calculator, I've already done these. But if you put them into your calculator, you're going to get a number of 3.132. For this, you're going to get a number here of 51.408. Here, if you multiply across, you'll get 1.197. And here, if you multiply across, you're going to get 0.174. So, take the mass number of the version, multiply it by the percentage of the version, you get a piece of the number that's going to contribute to the overall average atomic mass. So I got this piece, I got this piece, I got this piece, I got this piece, and then what you do is you take these pieces and you add them up. You take these pieces and you add them together. And when I take the 3.132 and the 51.408 and the 1.197 and the 0.174 and I add them together, I get a number of, hold on, should have had this done already, and I don't. I apologize. 55.911. I'm going to double check that, make sure that's right. 55.911. So let's do a double check together really fast to make sure that this is true. 3.1, clear. 3.132 plus 51.408 plus 1.197 plus 0.174. 55.911. So this is our average atomic mass. That's the appropriate averaging of all the natural isotopes with their percentages in mind. You take each mass number, multiply it by the percent, find the piece that's going to contribute to that average total. Do that for each isotope. Now sometimes you only have 2 isotopes, sometimes you have more. Get a number. Now, some of you are going to notice, that doesn't match that. And you're right, it doesn't. And it should, but it doesn't. This should be close. It is, it's close. But because of the rounding of these numbers and a little bit of a fib with these numbers that we're using, which is fine, and don't worry about the little fib I'm telling you. But because of these rounding issues, it may not match the periodic table exactly, but it should be close. And if you do all these numbers with decimal places way out to several places beyond the 10th place, and you work these out just a little bit more scientifically, you should end up with the number that is on the periodic table, or close. So, but I'm looking for this method. So I'm going to give you some of these, and I'm going to see what you can do with it, and give them a try. All right? Any questions? Get back to me. Thanks.